Hi, I'm Youngmin Kim from Seoul National University. Thank you for the introduction. And today's talk is about browser privilege escalation attacks using browser extensions. This work is done by me and my advisor, Professor Byoungyoung Lee. TLDR, what's possible with our attack? If the victim visits the attacker's site with this extension installed, the attacker can execute script on another site, steal cryptocurrencies, and steal passwords. How? Let's get started with how modern browsers operate. One unique aspect of a web browser is it renders remote content. It means the attacker can control what content is processed. As a result, browsers have put untrusted content in a sandbox process called render process, limiting the attacker's reach. Each step is rendered in a separate render process, and they are managed by the privileged browser process. However, the attacker can still load the cross-site data within their reach, the same render process. For example, an iframe of bank.com, which contains sensitive data like banking credentials, can be embedded within the attacker's site. Specifically, there are two types of attackers we considered. The first one is an attacker with read and write capability. They exploit a vulnerability in the rendering engine to execute arbitrary code. They can also spoof IPC messages to the browser process. Since the rendering engine is so complex, it's nearly impossible to be bug-free. Chromium team even assumes that determined attackers will be able to find a way to compromise the render process. The second is an attacker with only a read capability. They can access any memory address space within the render process using transient execution attacks such as Spectre, Meltdown, and I think there's an even new one to be presented today, Down4. In response, Chrome and Firefox implemented the site isolation. It renders each site in a dedicated render process. Now, browser security rests upon the OS process boundary, unless there are other holes. Searching for holes, we found browser extensions. Since the browser extensions are designed prior to site isolation, one needs to be done to better align with the site isolation. Browser extensions are the little tiny icon thing you see up there. They are third-party programs that can be installed to extend the browsing functionality. According to Chrome and Firefox, about 1/3 to half of their users install them. Extensions use plain web technologies such as HTML and JavaScript, so they have pages. Since extensions have its own origin, they also run in a dedicated render process. However, this one is special. Unlike normal web pages, they can access browser APIs and cross-site data as long as the permission is declared in the manifest file. For instance, cookies. Furthermore, to modify or interact with a page, the extension can inject a script to a page called the content script. It is executed in the same process as the page, as granting special privilege to the content script would mean granting the render process those privileges. The browser itself does not give content script extra privileges. Instead, extension developers should use messaging to communicate with the extension page to request the privileged actions. For example, if the content script needs cookie of the page it's in, it can request that to the extension page by extension message, like give me the cookie of evil.com. But let's bring the attacker RW to the picture. Remember, the content script runs in the page render, and the attacker RW can spoof IPC message. This means the attacker RW can spoof extension message too. For instance, modify the message to request the cookie of google.com. Hence, the extension page should validate the extension message using the sender field in the extension message. To make matters worse, we found several bugs in the browser that makes this sender field untrustworthy. Due to the time constraint, we will skip this one. And furthermore, there is a persistent data storage for extensions called extension stories. Both extension page and content script can access these stories. Let's bring the attacker RW back to the picture. Since content script can access the extension stories, so the renderer process, so the attacker. Therefore, there should be no sensitive data in the extension stories. However, for the sensitive data, there is no alternative. The documentation, the Chrome and Firefox documentation discourages from using storage that only the extension page can access. So the extension is left with only the extension stories. Finally, the content script is isolated from the page using software-based isolation in the JavaScript called isolated world. So the page cannot normally access the data on the content script. But remember, the content script is in the same render process. So the attacker RW and R in this case can access the data in the content script. Therefore, there should be no sensitive data on the content script. So we found these three requirements that extension should satisfy in order to match the site isolation. How well do developers meet them? Short answer, no. What happens if they don't? Privilege escalation attacks happen. We found multiple extensions failed to meet these requirements, leading to privilege escalation. First, there were vulnerabilities that allow reading sensitive data by spoofing the message or reading the extension stories or reading the content script memory. For example, password managers use content script to autofill the login field. Content script therefore requests the credential using the extension message. However, extensions don't validate this message, so the attacker can spoof this message and request credential for any site. Furthermore, we found that some extensions also store the encryption key that encrypts the password stories on the extension stories. So the attacker could steal the encryption key and therefore passwords. Next, there were vulnerabilities that allow modifying sensitive data by spoofing the message or writing to the extension stories. For example, ad blockers and user script managers like TemperMonkey allow injecting scripts to specific pages. This configuration is stored on the extension stories, which the attacker could modify. So the attacker can insert an arbitrary script like alert1 and perform universal cross-site scripting, or called USENIX. Finally, there were vulnerabilities that allow executing privileged APIs by spoofing the message. For instance, cryptocurrency wallets like MetaMask use pop-up to ask a user for an approval of a transaction. The pop-up also communicates using extension message, like if the user clicks the confirm button, it sends the message of approve the transaction message. But the extension didn't validate them, so the attacker can spoof an approver, signing an arbitrary transaction. In other words, the attacker can steal funds too. Likewise, we found similar vulnerabilities in 15 out of 21 extensions with more than 10 million users. Since the extension usage distribution have a long tail, these extensions account for most usage of extensions. So what's the problem? We attribute our finding to security requirements we found, the three security requirements we found that is imposed on extension developers. Extension developers are not security experts, and they do not consider this site isolation or these threat models. So therefore, we present a fist bump, a solution on the browser side, a new extension architecture. We move the content script logic to the extension process out of the attacker's reach. Instead, it uses DOM proxy to interact with the page. The DOM proxy only does what the page can already do, like modify the DOM and handle event, so no additional privilege is needed for the render process. To speed up, we implemented garbage collection and batch processing on Fistbump. Our implementation showed it is compatible with existing extensions without modification. In terms of runtime, it showed negligible difference in metadata and storage access. Since the messaging no longer needs IPC, it's shown decrease in runtime. However, since DOM operation now require an IPC round trip, it slowed down significantly. However, but with batch processing, we could bring this down to 13% overhead. So our summary is that current extension architecture imposes a difficult security requirements on extension developers. This lead to privileged escalation attacks, rendering the site isolation useless. So we propose fist bump, a new extension architecture that moves the content script to the extension process. Thank you.